Okay guys, next we have inductor filter, which is also called L filter. We can also call it series inductor filter. In this filter, here we have the rectifier, full wave rectifier, because we use two diodes. This is the full wave rectifier, and here we have the transformer. Across transformer we can apply the AC input to this transformer. So once this AC input passes through this half wave full wave rectifier, then in the output we have pulsating current or ripple DC current, which is given here. Its shape is this one. This is the output of this rectifier. It contains both AC and DC component. So here we introduce or connected this inductor, which is represented by this L. This is the inductor. This is the symbol for inductor. This inductor is connected in series with this load resistance. This is the load resistance. Now the current flowing through this inductor will pass through this load resistance, and across this load resistance we can calculate the DC output. So this is the circuit diagram of inductor filter or L filter. Now we know that the basic property of inductor is, like I think before we discuss about the inductor, that the inductive reactance of inductor is XL, which is equal to omega L, which is also equal to 2 pi FL. Now for DC current, frequency is 0. So the inductive reactance will be equal to 0. If I put F is equal to 0 in this equation, we get XL is equal to 0. So it means that this inductor offers zero resistance to the DC current. So once DC current, here we have both AC and DC current. Once this pulsating or ripple DC current flowing through this inductor, then this inductor will allow this DC current to pass through it. So DC current will easily pass through this inductor. While for AC current, the value of frequency F is finite. Its value is finite and non-zero. So if we put this finite and non-zero value here, then the inductive reactance XL value will be finite and non-zero. Now this shows that this inductor offer a high resistance to the flow of AC current. So we can conclude from these two equations, or from these two suppositions, that inductor allow DC current and block AC current. Now the blocking of AC current depends on this inductance L. If we consider an inductor with large L inductance, then it will block almost all the AC current. But if we use a inductor with small inductance, then there will be a part of AC current will flow through this inductor to the other side. Now we can explain it in another way now here, that inductor opposes, the statement is inductor opposes any change in any change in current flowing through it, that current which is flowing through it by producing induced EMF. What this statement means: when current flowing through inductor and that current tends to increase, then this inductor opposes the increase in current by storing energy in it in the form of magnetic energy, magnetic field. Like if the current flowing through this inductor increases, then this inductor opposes this current by storing energy in the form of magnetic field. At the same time, when current flowing through this inductor tends to decrease, then it opposes the decay of current or the decrease in current by taking that stored energy which was stored before when the current was increased away from the magnetic field. So which means that in both the cases, either the current increases or decreases, the inductor tries to minimize, inductor tries to maintain a constant current. Thus inductor smoothens the output current and reduces the ripple. So inductor opposes the increase in current by storing energy in the form of magnetic field. This is one aspect. Like if current is increasing, then this inductor will oppose the increase in current by storing energy in the form of magnetic field. Inductor oppose the decrease in energy, the decrease in current by releasing the stored energy. Away from the magnetic field. By this way, this inductor maintain a constant current, that it will not allow the current to be increased or not allow the current to be decreased. So it maintain a constant value of the current. So it smoothen the output current, and once the output current gets smoothened, then it means that the ripple will reduce. So we have two explanations for the flow of AC and DC current. Like DC current is constant, so once DC current flowing through the inductor, so it neither stored energy nor release that energy, because the DC current is constant. DC current is like this. But once this pulsating current passes through the inductor, so once the current increases, then this inductor stores energy in the form of magnetic field, due to which it opposes this increase in current. And once this current decreases, like this part start, then this inductor release that stored energy from the magnetic field to oppose this decrease in energy. So overall, this inductor tries to maintain a constant current. In other words, this inductor allows DC current and block AC current, and this is explained here. Now here we will discuss the working principle of inductor. The output of rectifier contain both AC and DC. If you look at here, this output of this rectifier contain both AC and DC component. When this pulsating current or this ripple current, which contain both AC and DC current, passes through this inductor, then the ripple will be blocked. Like this ripple, this variation will be blocked by this inductor. So the inductor block this variation or this ripple, while the DC component will pass through this inductor without any resistance or without any opposition. So overall in the output we have DC current. Now the output will be like this. I will plot it here. The output will be like this. Suppose this is the output of rectifier. And let's suppose this is the mean or average value of this current. Here this is the maximum value of the output voltage. This is the output of this rectifier. Here this rectifier. It contains both AC and DC component. This is the average value. We call it VDC, DC voltage, and its value we already calculated in the full wave rectifier. It's equal to 2Vm over pi. Now this pulsating current is without inductor or without any filter. Now once this inductor is introduced, then the output current, the output current in the across the load resistance or the output voltage across the load resistance will behave like this. Its shape will be like this. Which is denoted by this rate curve. So this is the output current when there is with inductor filter. Now there are still some variation, it is not exactly the straight line, but it's like this. There is still some variation, but we can minimize it by using an inductor with large XL value, large value of XL, inductive reactance. Now the period for which current flowing through this load resistance RL is lengthened now, because initially the period was this. Now the period is started from here to up to this point. Now the period was initially when without filter was this one, but here now the period now increases to this value. So the period increased by this much. The next period now started from here to up to this point, so it increased by this much. In simple full wave rectifier, the period of conduction of diode D2 start only after the current in diode D2 stops. Like once the period of diode D1 stops, then the current in diode D2 will start after that. But if we look at here, but in case of full wave rectifier with inductor, if we look at here, the period of the conduction of diode D2, the period of conduction of diode D2 will start here. Start before the current in diode D2 stop. So that's why the output voltage never drop to 0. It is always some value. Here the output voltage dropped to 0 when there was no inductor, but here the output voltage does not drop to 0. It is some value. It is because the period of diode D2 start before the current and diode D2 D1 stop. Now we will calculate the ripple factor of this inductor filter, so which I will calculate in the next video. So the length of this video is almost more than 15 minutes. Thank you.